Um, so here we have another sample problem. It says what is the electric potential at point P, located at the center of a square. So the distance d is 1.3 meter, and the charge Q1, Q2, Q3, and Q4 are those values. So actually it is nothing but, so you can see that this is d. So the distance between each charge and point P will be d over square root of 2. So it is very simple geometric problem. So d over square root of 2. So the v at point P will be summation of I from 1 to 4 vi. So it will be nothing but k times summation or Q1 over, maybe we can call this R. So Q1 over R plus Q2 over R plus Q3 over R plus Q4 over R. Because all the distance between P to Q1, Q2, Q3, and Q4 are all R, which is actually d over square root of 2. So k, so here, so this is nothing but k over R, Q1 plus Q2 plus Q3 plus Q4. So k is 8.99 times 10 to the 9th power. R is d over square root of 2, which is 1.3 over square root of 2. And then multiply by Q1 is 12 nano. Nano is 10 to minus 9. And then Q2 is minus 24 plus 31 plus 17. So V is 330 volts. So for point P is 350 volt, and actually this one is positive, 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 and negative. So it's also show the equipotential surface here, like this string shape. Actually, why it look like this is, it's not easy to answer, because actually you need to calculate the electric potential one point after another until you find, oh, this point is 350, this point is 350, and then you connect them together so that it forms the electric potential surface. But actually you can imagine this is a negative charge, these are positive charge, so this will be higher potential, electric potential. This side will be the lower electric potential. So you can imagine the equal potential surface. This side will be like that, But so next we have another sample problem. So we have 12 electrons of charge minus E are equally spaced and fixed around a circle, radius R. So this one, like a clock. So relative to V equals 0 at infinity, what are the electric potential at the center due to this electron? So V is nothing but Q times. So this is the distance is capital R, and actually there are 12 electrons. So we have a minus 12 E. So you can write it as minus 12 KE over capital R. And that's it. So now it asks you if the electrons are moved along the circle until they are uniformly spaced over 120-degree arc. What then the potential at C? How does the electric field at C change, if at all? So actually for the electric potential, it is still the same, minus 12 KE over capital R. It doesn't really change because it's only related to the distance between them. So you suppose Q doesn't change, R doesn't change, QK and RK, the ratio doesn't change, and you add all of them together, then the total electric potential will not change at all. However, for the E field, you can imagine that for this electron, the E field will point it upward because it is a negative charge, and for this one, it will point this way. So they will cancel. So all of them will cancel. For this case, the E at point C will be zero. However, for this one, as long as they are uniform distributed, so the E field will point to this way. The E field will point to this way. So one important concept is that even at point C, they have the same electric potential. It doesn't really mean that the electric field at that point is the same. Usually not, except the case that all the geometric shapes are the same. So any questions up till now? So next, we consider the potential due to the electric dipole. So I suppose you have already familiar with the electric dipole. We have the dipole positive charge and negative charge here with a distance small d. So now we evaluate the voltage or electric potential at point P. Not necessarily on the x-axis, not necessarily on the z-axis at the point P. And now we assume that the angle is theta. Still, we need to assume that this point is sufficiently far away, which means that D is much R is much larger than D. So this is much far away, so that we can make an approximation that R plus and R minus are parallel to each other. It's similar to you assume the sun is infinitely far away, so that the sun ray are parallel. So now we assume this line and this line are parallel to each other, and in this case this is R plus, this is R minus, and as long as they are parallel, so you can assume that point P is here, point P is here, and point P is also there, out of the screen. I cannot write there, but actually, as long as you assume that they are parallel, you will assume there will be 2 point P. It's very strange, but actually that is how it make the approximation. So this length is R minus R plus. R minus R plus. So we have V equals V plus V minus. And it will be nothing but K times Q over R plus R minus Q over R minus. So Q can be factored out. We have Q here, and then we add them together so that we have R plus R minus in the denominator, and then R minus over R plus at the numerator. So this is actually this one. So now we approximate R plus times R minus to be R squared, because R plus is R. R is here, R plus is here, R minus is here. So if R is much larger than D, so this R squared will be approximately R plus times R minus. And R minus R plus is D cosine theta. So this is D, this is D, this is theta. Because if we assume that this one is parallel to this one, then this is also theta. This is also theta. So D cosine theta is approximately R minus over R minus R plus. So we make this approximation, and then substitute to here, so that we have V equals Q over 4 pi epsilon naught times D cosine theta over R squared. And if you still remember, P is the dipole moment, which is Q times D, so that we can also write it as K times P cosine theta over R squared. Any questions? Okay. So similarly, we consider the potential due to continuous charge distribution. So now we cannot use simply algebraic sum for the total potential. We need to evaluate. We need to separate the charge into many small charge packets, and then we evaluate, divide the distribution into charge element dq, and then we calculate the dv according to this dq, which is originally we have a v equals k times q over r, so that now we have a dv equals k times dq over r, and then we just put it here, so that the total v is the integration of dv, and then plugging in dv equals k times dq over r, so that it becomes this way. This one is a constant, so that we only consider this integration. We now examine two continuous charge distribution, a line and a disk. So similar to previous case, first we consider the line of charge. So we have a line of charge here, and then we consider the potential at point P. So the total charge will be Q, or maybe, yeah. Now here we have a thin conducting rod of length L, as shown in figure B. The element of what has a differential charge dq equals lambda dx. dq is equal lambda dx. So lambda is the linear charge density. So dx, we have a dq equals lambda dx, and then so dv is nothing but k times dq over r, and then so this is dx. So dq is lambda dx, and then r is this one. So it will be, this is a right angle triangle, so r is d squared plus x squared. The whole term take the square root. So according to the Pythagorean theorem, so we have the dv like this. So we calculate v by integrating dv from 0 to L, because this is x, which means that this is the original point of the x-axis. So we integrate from the 0 to this point is L. So actually we need to calculate this integration. But actually this should not be very difficult, or you can just check it on the integration table, so that you finally find the answer to be this way. Or, well, I can just quickly go through how to evaluate this one. So you just assume x to be d tangent theta. So dx is d secant square theta d theta. So x squared plus d squared will be 1 plus let me see, d squared 1 plus tangent theta. So it will be d square secant square theta. So this one take the minus 1/2 power, so it will become 1 over d secant theta. So in this case, the original integration, it will become let me see, this one will be d secant theta inverse, and then dx is this one, so d secant square theta d theta. So we cancel all of them, cancel d, and then we leave the lower and upper bound. So actually, we know that tangent theta is x over d, which means that we can draw a y angle triangle, so that this is theta, this is x, this is d. So this is x squared plus d squared, take the square root. So if x is 0, then this one is 0. And if x is L, x is capital L, so this is, we call theta L. We call it theta L, and theta L is nothing but arctangent L over D. Theta L is L over D. So we leave it there. So now we have 0 to theta L, integration of secant theta d theta. So we need to calculate this integration. So we can multiply it by tangent theta plus secant theta in the denominator and the numerator, plus secant theta. So this one becomes secant theta, tangent theta, and secant square theta. So this will become d tangent theta plus secant theta, and then we have tangent theta plus secant theta at the denominator. Yeah. So we have, this is log because this is an inverse function. So we have log of secant theta plus tangent theta. Take the absolute value, and then we evaluate the theta L and 0 and subtract them. So for theta L, secant theta is secant theta L is x squared plus d squared square root over d, because cosine theta L is d over this one should be L. This one should be L squared. Should be like this. And then tangent theta L should be L over D. So this would be log of L squared plus D squared plus L all over D. So this is the antiderivative, evaluate at theta L, and then minus it evaluate at 0. When we evaluate at 0, which means that secant 0 degree is 1. Secant 0 degree is 1. Because cosine 0 degree is 1, so secant theta degree is 1. And the tangent 0 is 0. So log of 1 is 0. So that finally it becomes log of L plus square root of L squared plus D squared over D, like this. So we have calculated this integration. So next we consider the potential due to a continuous charge disk. Charge disk. So so here we have dq on this orange ring is 2 pi r prime dr prime times sigma. Sigma is the surface density, surface charge density, and then this one is the area. So you can similarly, you can try to cut this and then you flatten it so that it will become a rectangle. And then the height of this rectangle is dr prime, and then the width is the parameter, which is 2 pi r prime. So we have this area, 2 pi r prime dr prime. So similarly, we have dv equals to k times dq over r, and then we substitute dq to be this expression, to be here, and then r. This is r, which is the distance from this ring. The distance from this ring to point P, we consider. Point P is actually on the z-axis. So R should be z squared plus capital R squared, and then take the square root due to the Pythagorean theorem. So we have R here. So similarly, we calculate V by integrating the dV from 0 to L, because R prime from 0 to capital R will be the whole disk. To R. Let me see. So this one should be R prime. 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 This one should be R. This one should be R. So this integration is easier because it is nothing but sigma over 2 epsilon naught 0 to R, and then we apply the chain rule so that it is 1/2 d R prime square. So we have a c square plus r square here, and then r square, and z is actually a constant, so we can just put it there. So we have this function, we have also this function, and then take the 1/2. So we can use the integration of a polynomial function so that we can get this answer. So V is like this. Note that the variable in second integral is r prime and not zero, and not z. So dr prime. So any questions? Any questions? Okay, so so this is the expression for the potential of a charge disk. So next we consider another property. So now suppose that a positive test charge Q0 moves through a displacement ds. So we have ds here in an E field at this point pointing to this side, and then the angle between them is theta. So the electric field does on the test charge during the move is minus q dV, which is the negative of the potential energy change. So F dot ds is the work, and we know that F is the electrostatic force, which is Q0 times E dot ds, so that we can so actually we can change this one is the work done, this one is the work done, this one is also the work done, so we change it to this term, and then for the right side Q0 here, and then E dot ds is E ds times the cosine theta. So it turns out to be E cosine theta equals minus dV ds. Yeah, or this is E. So if you project this E on this s-axis, so ES will be E cosine theta. So you project the E on the s-axis. So this is actually ES. So we can write it as ES equals minus dV ds. Take the derivative, minus the derivative of the electric potential with respect to the displacement. So generally, or in the Cartesian coordinate, so we can write it as Ex equals minus dV dx for y, for z, and we have three equations, and if we write it as a vector form, it will look like this. The E vector, the E field is the minus the gradient of V. So in Cartesian coordinate, gradient can be written as d dx or partial x I plus d dy j plus d dz k. So actually V is a scalar field. You can actually evaluate all the electric potential over the whole space. So actually V is a scalar field, E is a vector field. So this gradient, we call it this one is the gradient operator to make the scalar field into the vector field. And later on you will see this gradient operator later, but it will something like a gradient dot, gradient cross, something like this. You will see it in chapter 32. So actually we can write it as the gradient operator. Yeah. So actually, previously we learned that V is the line minus the line integral of the E field over the path. And now we can write it as E is the minus the gradient of the V. So actually this is a fundamental theorem of calculus for line integral. Fundamental theorem of calculus for the line integral. Actually, when you learn the calculus, you know that if you have, let me see, if you have f of x equals f prime of x, or df of x dx. Then the fundamental theorem of calculus tells you that f of b minus let me see, f of b minus f of a equals f of x dx from a to b. So this is the fundamental theorem of calculus when you learn the calculus 1 or whatever. So this is another form of the fundamental theorem of the calculus. This is for the line integral, and later on you will also see it for the surface integral, or for the triple integral, something like that. So we have a sample problem. So just now we derive this expression for the charge disk, for the potential of the charge disk. So now it tells you that the electric potential of the charge disk on the central axis is this expression. Starting with the expression, derive an expression for the electric field at any point of the axis of the disk. So we can calculate Ez is minus dV dz using this one, because we only consider the z-axis, the point P only on z-axis, and actually this v is only related to z but not related to xy. So you can simply imagine that when you consider Ex equals minus dV dx, this expression is independent to x, which means that the x component should be 0, and so as Ey should also be 0, which means for the E field on z-axis, there will be no xy component, only z component. So we can just take the derivative. Let me write it like this. So we have a negative sign, so we have a d dz, and then as long as we have a negative sign, so we can simply write it out. This is constant, so we can just factor it out. So we have d dz, z minus square root of c squared plus r squared, something like this. So dz dz is 1 minus, this one is z squared plus r squared to the 1/2 power. So we take the derivative is like 1/2, and then this 1/2 power will minus 1, so that it goes to the denominator. And then chain rule, we need to take the derivative of the argument, so that it becomes 2z. So 2 and 2 cancel. So it turns out to be sigma over 2 epsilon naught 1 minus z over square root of z squared plus d squared, r squared, like this. So if you still remember, we in chapter 22, we calculate this E field using the separation and integration for the E field. Now you can imagine that this integration is slightly easier than integrating the E field directly, because V is actually a scalar field. V is a scalar, so that when you just integrate, you don't need to care about the vector decomposition over x-axis, y-axis, z-axis, because it may makes you make mistakes. So at least calculating the V is easier than calculating the E directly. And after obtaining the expression for the V, then we can simply take the derivative. Derivative should be easy to all of you, I think, at least easier than integration. So you do a easier integration and then take the derivative, and then you will finally get the E field. You'll finally get the E field. So this is why we need to consider the electric potential rather than just all go to the electric field. So let's